me introduce our speaker then to move along here. It actually gives me great pleasure to introduce Dr. David Rosen. I've actually known David since his days as a graduate student at Memorial University back in the late 80s, early 90s. David did his undergraduate work at Guelph University and subsequently his master's and PhD at Memorial University. He's currently a professor at the Institute for Oceans and Fisheries at the University of British Columbia. Dave's work has focused and continues to focus on the energetics and nutrition of marine mammals. These are actually topics that are quite dear to my research background and interest as well. So I've paid close attention to the work David has done over the years. Many of his studies are focused on marine mammals in a captive environment where he has the ability to use or train or use trained animals to do things that would be difficult to do in a situation in the wild. Dave's work is both oriented towards conservation issues and towards the basic advancement of knowledge and theory. He does tell me he's not a walrus expert, but nonetheless, we're going to hear from him about walruses tonight. His talk is entitled, "What Does It Take to Power a Walrus? Predicting the Effect of Climate Change on Food Requirements of an Iconic Arctic Species." His talk is based on his paper in Marine Mammal Science that was published in the January issue, and that was entitled "Resting and Swimming Metabolic Rates in Juvenile Walruses." Just so you know, that paper has been given open access. It actually was opened up a week before the talk tonight, and it will be open for another week if you don't normally have access to the journal and would like a copy of his paper. You can get it without having to pay for it. So we'll also be recording the seminar tonight, and that recording will be available on the Society for Marine Mammalogy website in about a week's time. So with that, let me turn it over to David and hear what he has to tell us about walruses. David?
Thank you very much, Daryl. And thank you to the Society and the journal people for inviting me to give this talk. And thanks to everyone that showed up for yet another Zoom or Zoom-like meeting in their long day, month, year. So today I'm going to be talking about some science that we did with some young walruses here in Vancouver, Canada. But before that, there's one really important aspect that we want to get out in the open. And that is, why walruses? Charles Lippmann actually asked me this, and why not walry would be the question. And the shorter answer is because they're not Latin of derivation. I always was told it was walruses because it was Greek origin. That is apparently also a lie. As far as the etymology goes, that most people agree that it actually comes from the Scandinavian or Danish, walrus, meaning whale horse. So really, if we were using the origin, we should be calling the plural of walrus, walrusin, but that's never going to happen. The real reason we say walruses is because it's English, and that's what we do with US in English. I actually think the Latin name, which translates to tooth-walking seahorse, should be used as the common name. I think that's one of the more exotic names we have. But that's just one of many digressions I'm sure I'll get into today. So as Daryl mentioned, the talk is based around a paper that recently came out in the journal Marine Mammal Science. It talks about some experiments we did with 2 juvenile walruses. And even though these studies were done with walruses at the Vancouver Aquarium, the purpose of these studies was really to help with the conservation of animals in the wild, particularly to understand and to help scientists forecast how global climate change might be affecting or affect in the future this species. A little bit of a primer about walruses. that they are a true Arctic species. As most of you know, there are, depending on who you ask, 2 or 3 distinct subspecies, the Atlantic and the Pacific. As far as numbers, walruses apparently are notoriously difficult to count. The counts vary widely. In the Pacific, could be 140,000, could be 200,000. Much smaller in population size and physical stature are the Atlantic walruses. There's about 25,000 of those. Because of the unknowns regarding the numbers, the classification for the conservation status is a little up in the air as well. According to the IUCN, the Atlantic are classified as near threatened and the Pacific are data deficient. But they are an Arctic species, which means that they're subject to whatever changes are happening in the Arctic environment. And as I'm sure everyone on this call knows, the polar regions are changing at a tremendous pace, faster than anywhere else on the planet. And one of the most prominent environmental changes that we're seeing is the decrease in the extent of the summer ice cover, as shown by this illustration. Why is that important, particularly for walruses? Well, walruses, particularly females and their young, they're an ice-dependent species. And the females and the young are really dependent on these stable ice flows, particularly in the summer reproduction period, when they're nursing their young to rest, to haul out, to not be in the water. The other benefit of these stable ice platforms is they tend to be conveniently located over the continental shelf break on these sort of prime foraging areas. And so by happy coincidence, walruses, female walruses, do not have to travel very far to forage, which means they don't have to expend very much energy, and they don't have to keep their young, they don't have to be away from their young for great lengths of time either. It's a sort of short trip down to the corner store. Now, one of the obvious implications of a decreased extent of the sea ice is these foraging grounds are now further away from where the walruses want to haul out, which means you have to spend more time in the water, you have to expend more energy getting to the foraging grounds. And that, in fact, also means you need more food because you're expending more energy. So it's kind of a vicious circle, which raises the sort of quantitative question of, does it matter? Like, what is the cost of this behavioral change? How much of a burden is it to individual animals? Which brings us to the central question of the talk and the research is, what is the energetic effect of these environmental changes on individual walruses? Or if you look at another way, how do changes in behavior translate into changes in energy or food requirements? Now, this isn't the first time this question's been asked. It's a standard question in physiological conservation. And it's very well illustrated in this figure from one of Mark Udovitz and colleagues' papers that was looking at walrus movements. And this flowchart sort of shows you that there are environmental things you can measure, like sea ice availability. And then you can measure what the animal is doing in reaction, assumedly, to those changes in environmental conditions, whether it's movement across the landscape or changes in what they're doing at any particular point. But how to take that next leap, how to change those, how to translate those behavioral changes into energy. And energy is an important currency to use because it's probably what's going to impact things like physical health and body condition, which will ultimately impact population parameters like survival and reproduction. The problem is translating these changes in behavior or measuring how they affect the energy required or the food intake is very difficult to do in the wild for obvious reasons. So what tools do we have as scientists? Well, one of them is bioenergetic models. What is a bioenergetic model? The bioenergetic model is this more or less complicated computer simulation where you build a literal walrus within the framework that you can manipulate in space and time, which sounds very complicated and very science fictioning. But really the end result is pretty simple. And it's epitomized by a figure like this, where on the y-axis, we have what we're interested in, either energy or food requirements. And then along the x-axis, along the bottom, we have various conditions, whether it's the age of the animal or the season or even the extent of the summer ice cover. And what our model does is give an output for what the total energy requirement is under those particular conditions. It can be for an individual animal, it can be for a population, however you want to use it. Underlying this total output is really what you're doing is adding up all the different aspects of an individual animal's energy budget, understanding how they interact, and then summing them together. And those individual components of an energy budget can be sort of visualized through these different color bands. And the math can be quite complex underlying it, particularly the interactions. But the concept is actually pretty simple. And there's a whole bunch of components for an animal's energy budget. But really, one of the most basic components is something called resting metabolic rate or resting metabolism, and it is literally the foundation of an energy budget. It's the amount of energy an animal expends when it's not really doing anything. You could almost say it's the cost of existence. So energetically, it's the foundation of an energy budget, but it's also important because it's the foundation of a model, because resting metabolic rate interacts with and actually can be used to extrapolate different costs within your model. The problem is, of course, if you have any errors or biases in your estimate of resting metabolism, these can be multiplied throughout your model and vastly change the output. Another important cost in an energy budget is the cost of movement. We're going to call the cost of locomotion. And that's particularly important because it's probably the largest voluntary cost in most animals' energy budget. And in most animals, the amount of movement they do is going to affect how much energy they required, but it's also tied to their foraging. So you have almost this, again, this circular relationship between how much you have to forage to get your energy requirement and then the cost of that actual foraging itself. What the locomotion component allows us to do in the grandest scheme is really it's the basis of translating a lot of those behavioral changes that we observe in the wild into the currency of energy. So it allows us to understand in the grand scheme of things how environmental changes are most likely affecting the total food requirements of an animal or a population. Now, I want to emphasize that there are some excellent published bioenergetic models, specifically where walruses are concerned. But it's also important to realize that the value or the precision of any model is limited by the inputs to that model. So optimally, what you'd want to do is have empirical measurements of every aspect of an energy budget specific to that species under those conditions. And we know we're never going to get there. So we have to extrapolate. And sometimes we have to extrapolate to other species completely, based on the perception that these are likely pretty similar in this respect. So we might substitute species A for a species of interest. Another resource that we can use is to take measurements of animals that are essentially in a laboratory setting. And those are animals that are largely in zoos and aquariums, where we can do controlled empirical measurements of these animals. So they're an alternate but valuable source for obtaining the data we need to go into these models. So you know where this is going. I'm going to be talking about some studies that we did at the Vancouver Aquarium with 2 walruses that are under human care. And these 2 walruses are called still Balzac, a male, and Lakina, a female. And they were born in the spring of 2016 at the Quebec Aquarium. And they are actually the first 2 successful walrus births in Canada, and I'm led to believe that there's only a handful of successful walrus births in any aquarium in the world. They were transferred to the Vancouver Aquarium, where I do some of my research, just in time for Christmas in 2017, when they're about 18 months old. And the studies that I'm going to talk about today, the data was actually collected over a period when they were at about 2.5 to 3.5 years old before they were transferred back to the aquarium to Quebec. What we did might be obvious from either my paper or the introduction, is we measured the energetic costs of 2 components of their energy budget, resting metabolic rate, and the cost of swimming, which raised the question of how do you measure the energetic cost of an activity? Well, if you're an 18th century biochemist, you surround them by ice and do direct calorimetry. It's not really feasible with a walrus, and there's a lot of irony about measuring how much ice a walrus would melt given the effects of climate change. So instead, our go-to tool in marine mammal science is respirometry, which is based on a relationship between how much oxygen you consume and CO2 you produce and how much work your body does. So the heat to oxygen relationship. Now that sounds pretty simple. How do you actually do it with a walrus that weighs a couple of 100 kilograms? Here's some video, one of the training sessions with our 2 walruses at the back research pool of Vancouver Aquarium. And we'll see what they trained them to do was to sit quietly under this floating respirometry dome that I'm holding. And they sit there quietly at the side of the pool for a sufficient amount of time that we can measure a steady state for how much oxygen they're using and CO2 they're producing, because this whole system sucks air through the system and then it all gets analyzed at the other end for gas. The key is the animals have to be calm. And in this video, you'll see the trainer reinforcing the behavior of the animals, which is really important. The trick, of course, is that you can't feed them when you're doing the actual trials just because of physiological interactions. So it took us about 3 months to train this behavior to the point where the animals were not moving and totally calm. We continued to train over the next year, but about every 2 weeks, we did an actual measurement. And we did it over a 13-month period because one of the things we were interested in was looking at changes in their resting metabolic rate throughout development and over different seasons. Now, that's resting metabolism, which kind of seems easy compared to the cost of swimming. And measuring the cost of swimming in an aquatic mammal is very difficult. And in fact, there's very few measures of the metabolism of swimming among marine mammals, partly because of logistics and partly because as physiologists, we're more sort of captivated by their diving ability, which is pretty spectacular, and the costs associated with that, but is physiologically different than swimming distances. So how did we actually accomplish this with our walruses? Well, it was a lot of trial and error at first. And after a couple of months, we actually stumbled across what turned out to probably be the easiest behavior, which is we had them swimming laps of our large research pool. So they swam from diagonally corner to corner. And each lap was about 37 meters, and they swam 3 laps for every trial. And the trick was training them to do this consistently, to swim in a straight line without pause, without distraction. And the biggest trick was while they're swimming these laps, they can't breathe at the surface. We want them swimming at the surface, but not breathing at the surface. At the end of these laps, which is 110 meters, about the length of an American football field, they come back into the dome, as you maybe see this walrus doing. We measure how much oxygen they're using on the return, and through some fancy math, we can figure out how much oxygen they were using in their body during the swimming portion of the trials. Now, that actually simplifies things because you have to remember we're dealing with juvenile animals. We're essentially 200 or 400 kilogram toddlers. And if you have any experience with young animals or young humans, one of the rules they live by is everything is a game and everything is a toy, whether you intend it to be or not. And that includes both the toys you give them for amusement and your very specialized, very expensive scientific equipment. Here's the male walrus Balzac deciding that he would rather play with our metabolic dome than do a trial. Fortunately, we managed to disconnect the air hose and everything else from it. So there was no disastrous loss of several tens of thousands of dollars of equipment, but it's almost back to square one. This is the problem. We want them to be comfortable with this equipment, but sometimes they're too comfortable. In fact, I would say the axiom of a juvenile walrus is I don't take anything seriously. And to sort of illustrate this point further, I'm going to show you a clip of my friend and colleague, Sean Noren, who is giving a very serious interview about the importance of walrus research. And just behind her is the walrus pool. And we'll see that the walruses were not prepared to take the interview process as seriously as Sean was. Yes, that was a giant walrus spit. Before I get to the actual results, I'd like to give you this quote from Robert Heinlein that says, "If it can't be expressed in figures, it's not science, it's opinion." And I have two reasons for putting up this quote. One is I find if you put up an impressive sounding quote, people assume you're well read. The more pertinent reason for putting up this quote is it's one thing to measure the energy expenditure when animals are doing a certain behavior, but there are myriad of ways you can express that energy expenditure, depending on the type of question or the type of information you want. And it can get confusing, and it can also seem to give you contrary results. But you have to remember that you're expressing the data in particular ways for particular reasons. So I'm going to show you some iterations of some of the data, and you'll see the process we go through and how you can get different types of information from the same type of data. So for looking at resting metabolic rate, this is the raw data that we acquired over 13 months from the male and the female walrus. The male is in the blue triangles. The female is in the red circles. On the y-axis is resting metabolic rate. It's just in megajoules per day. It's just an expression of rate of energy output. And if you take a cursory look at the data, you'd make conclusions such as metabolism seems to increase with age. And generally speaking, resting metabolic rate for the male is greater than for the female. But of course, everyone in this call is smart enough to realize that there's some problems with interpreting it straight away as that. And if nothing else, we know that generally the walruses, because they're growing, are getting larger over the trials, and the male is larger than the female. So maybe that explains the trends we're seeing in the data. Well, how can we explore that? Well, one of the ways we can do that is to say, well, how much energy are the walruses expending per kilogram of body mass? And this is the same data looking at what we would call mass-specific resting metabolic rate. It's just the same rate expressed per kilogram body mass. But we seem to see the opposite results, where in this case, mass-specific metabolism for the female is actually higher than that for the male. So depending on the question we're asking, we get a slightly different result. Now, this manipulation, which is a very common one that we do in physiology and energetics, make some underlying assumptions about the relationship between energy expenditure and body mass. And that's where we get into this peculiar measure that I've largely only seen in the science world of marine mammals, which is a sort of fake unit called the Kleiber. And going back to some basic physiology that you may all know was the Kleiber is based on Max Kleiber's finding that there was a very strong relationship between the rate of heat production of a mammal and body mass across different species, a huge range of species. It's the famous mouse to elephant curve. And this you can think of as the standard for terrestrial mammals. So if an animal falls right on this line, you would say it is 1 times Kleiber. If the measured rate of heat production is twice of what you would predict from the line, you might say it's 2 times Kleiber. So it's a way of putting your rate of energy production as a ratio of what Kleiber might predict for terrestrial mammals. We can do that also for that same raw data for the walruses. And when we express it as this way, perhaps a better way of accounting for body mass, we see there actually is no difference between the males and the females. They're almost identical, they overlap. But the other thing you notice is on the y-axis, at the very bottom of the y-axis, is 1 times Kleiber. So that is where you would expect terrestrial mammals. So it appears that they're all way above the terrestrial mammal expectation. It's a little hard to visualize. And the question might be, okay, so they're higher than terrestrial mammals. I've read many places that marine mammals are way higher than terrestrial mammals. Are they higher than other marine mammals? Or, put it in the context of marine mammal species. And for that, I'm going to show you this graph, which is taken from Randy Davis's excellent new book on marine mammals. And this figure, all the little dots on this figure, again, this is showing the rate of energy expenditure on the y-axis, which is expressed as basal metabolic rate, which is similar to resting metabolic rate. I won't go into the details now. And on the x-axis is body mass. So it's very similar to what we saw with Kleiber. And all the little dots are mammals from the order Carnivora that are not marine mammals. And then all the big triangles are data that Randy has gleaned from the literature for basal metabolic rate of various marine mammal species in the big triangles. And you can see pretty well, without exception, that all marine mammals are higher than what you would predict for other members of Carnivora compared to terrestrial mammals, with the weird exception of the Florida manatee. Where do walruses fall? Well, they fall exactly where you would expect for other marine mammals. So you might conclude walruses for resting metabolic rate are no different than other marine mammals. But the problem is I kind of lied to you. I told a little bit of a fib, because all these other data from marine mammals are for adult animals, and we're dealing with juveniles. And we know that among mammals, young animals are going to have higher metabolic rates than adults on a mass-specific basis. Usually in modeling, we might use a figure of 2 to 3 times what we'd expect for adults. So based on that, we would suggest that, in fact, walruses do have, juvenile walruses have a lower than expected resting metabolic rate compared to what we predict for other pinnipeds. What about this swimming, the results from swimming? Again, it depends how you are representing your data. So the first data I'm going to show you is just the cost of data for all the trials for the males and the females, expressed as the absolute rate of energy expenditure. And these trials were done over about a month or a month and a half, just shortly before the animals were sent back to Quebec. So we're not going to worry about any time differences in these. The data were very, very consistent within trials for both of the animals. Their swimming speed, their energy output were very consistent within the trials that we did. The male consistently swam at a faster rate than the female, and it would appear that the rate of energy expenditure was higher for the male than the female. But again, there's some other things to consider in the data. First of all, as I mentioned, the male swam faster, and we also know that the male was larger. So is there a way for controlling that? Yes, we can recalculate the data to ask the question, how much energy does it take to move 1 kilogram of walrus 1 meter? So that's going to account for differences in body size and speed, hopefully. And when we do that, it looks like there's no differences between male and female, okay? So they have pretty similar cost of swimming on a mass-specific basis if they're going to swim a certain distance. But these numbers on the y-axis are pretty meaningless. What the question we probably want to ask is, how good is their swimming compared to other animals? Well, here you go. Here's a graph showing the cost of swimming expressed per kilogram body mass as a rate of energy expenditure over body mass on the x-axis with various species marine mammals. Again, unfortunately, there aren't a lot of data points for this cost of swimming in marine mammals. And it would appear that the 2 dots for the walruses, the red and the blue dot, are above the line of what we predict for other marine mammals of a similar size. Now, you might look at it and go, well, yeah, it's higher, but it doesn't look that much higher. You have to remember this is a log-log scale. And so, according to our calculations, assuming the animals are swimming at an optimal swimming speed, the cost of transport for walruses, for young walruses, would appear to be twice what we predict based on data from other marine mammals. Why is that? Well, there's a lot of speculation of why the cost of swimming might be higher for walruses. This is some video that I stole from YouTube that was taken off of the coast of Svalbard. And you can decide for yourself, whether they have the same grace and efficiency that you might expect for a marine mammal. One thing you should notice, it's really interesting, is they swim primarily with their hind flippers propulsion, just like a phosid seal, not like an odoriad, which raises all sorts of interesting questions about phylogeny and development. This video was accompanied by one comment that stood out from somebody with the clever name of XX, crap name XX. I thought that maybe seeing these creatures underwater would make them look more graceful. I was proven wrong. I think that's a little harsh. So you've seen the data. what can we say based on that data? What are the implications of our research findings? Well, let's talk about resting metabolic rate, which appeared to be lower than we'd expect for juvenile animals. And all other things being equal, we would expect if animals have a lower resting metabolic rate, then their costs are going to be lower overall. But can we use our previous modeling to explore that? Yeah, we can. We can put these lower estimates into some existing bioenergetic models for walruses. And we can say, okay, if we use these values versus the values that scientists were forced to use because there wasn't any empirical data, these lower rates of metabolism would translate theoretically into a decrease in overall energy expenditure of about 15%, which is not insignificant. But it may be insignificant compared to the higher cost of swimming. So the question is, what is the cost of these transiting or swimming across locations, particularly compared to what we thought the cost would be before we had this empirical data? Now, estimates in the literature of the metabolic rate of walruses when they're active have a huge range, tremendous range, about 3 to 6.8 of this Kleiber ratio. If we translate our data that we got in the laboratory, our estimate is at the upper end. It's about 6.5 to 7. And curiously enough, this is also almost overlaps completely with the only set of field estimates obtained from walruses in the wild are at this upper end as well. And so if we put these higher costs into these models, it's going to translate into higher overall costs, which suggests that the impact of these changing ice conditions, as far as having the energetic costs of having to move further, are even higher than we might have previously modeled. Now, I'm being very careful how I state that, because I want you to understand that the importance of this is not finding new data or different numbers than what have been previously suggested to use in models. What we're trying to do is come up with some actual measured numbers. If they're exactly the same as those that have previously been used in the models, that's fantastic. If they're slightly different, great. The idea is just to have greater confidence in these models, because these models will spit out a number. And even though the scientists are doing their best to come up with the best possible number, the more data that is relevant that we can put into these models, the better. And that leads to my point that these animals that are held under human care are actually a great resource as far as doing science and asking specific scientific questions under what are essentially laboratory conditions. And so they're really a fantastic resource for asking a whole bunch of questions if you're asking the right questions and doing the right sets of measurements. So not surprisingly, when these animals were at the Vancouver Aquarium, I had the opportunity to conduct a whole number of studies that I'm not going to talk about specifically. These are some photos of doing some very fine scale measurements of the tusks of walruses. And of course, male and female walruses both have tusks. This was part of an isotope validation study that we were taking part of. And here's some video, I hope it's not too jerky, of the walruses when they first came to the aquarium, and they were training them to do morphometric measurements. So measuring their body size and their body dimensions. And we did some ultrasounds as well to find out where their fat deposits were. And this is all part of trying to understand how their body changes, how it might change under different conditions, and how to best measure the physical condition of animals in the wild. I'm always amazed that this like 200 kilogram animal is just listening to these trainers who probably don't even weigh half of that. So that's all I want to say about the science itself today. I did want to finish up with a thanks to the Society and the journal for inviting me to share the research and photos of these two extraordinary animals. And also I wanted to thank the training and husbandry staff at the Vancouver Aquarium, who were significant partners in getting this research accomplished.
Excellent. Thank you, David, very much for that interesting talk. I'm going to turn it over to Eric if there are questions in the Q&A, and if not, I'll have a couple I might ask you a little bit later. Go ahead, Eric.
All right, I'll start with the first question. Thank you so much, David, for that wonderful talk. From Anonymous.
That's always a good sign.
You mentioned field measurements of walrus metabolic rate. How is this collected in the field?
Yeah, this was done using doubly labeled water. And so you're looking at the chemical turnover and making a bunch of extrapolations of how those chemicals change in the body the more you respire. So the more food the more food you take in. So the trick with doing those measurements is it can be very expensive because you're injecting chemicals, but also you have to recapture the animal. So you have to capture them, put in injections of these chemicals, and then capture them again and look how much of those chemicals are left in the body. So it's very difficult. The other thing is the animal is doing a whole bunch of things over that measurement period. And so the trick is to get enough measurements so that you can extrapolate why this animal is using more energy than that animal as it relates to how much they're swimming or how much you're diving. So it's great because you're doing measurements of what they're actually doing in the wild, but it's logistically difficult, it can be expensive, and it's very difficult to extrapolate the results.
All right, next question here from Mary Keenan. Great talk, thank you. What do you expect the metabolic rates and costs of swimming to be in adult walruses?
I'm glad you brought that up because I meant to mention that there is a parallel study being conducted by a very good colleague of mine, Andreas Fallman, with some adult walruses. And I don't want to take his thunder away. I think he's about to come out with those results. All I'm going to say is based on the studies he's done studies of both resting and swimming. I think the relationship between what we're seeing in juvenile walruses and what we're seeing in adult walruses is different than we'd expect. But I don't want to give too much away because it really is sort of Andreas's prize to present to the world. But I think it's coming out very shortly.
Okay, so look out for that soon. All right, next question from Edward Wong. Are there certain aspects of climate change that lead to reduced energy requirements for walruses? For example, if the walruses live in a warmer environment, do they save a significant amount in heating energy costs?
That's an excellent question. I don't know if anyone's actually looked at the thermoregulation of walruses. My contention would be that they probably, thermoregulation probably isn't a concern for walruses. So they probably, living in a warmer ocean is probably not going to give them any benefit just because they're so well insulated. I think that probably one of the big questions as far as, that we don't have a great handle on because it's a very complex question is, as it's not just the temperature of the ocean, but it's also, of course, the salinity and all the biochemistry that's changing. And how is that going to affect their prey fields as well? So we can calculate what the energy requirements are for getting to these prey fields. But if these prey fields are changing in their abundance or their location because of changes in water chemistry, that's going to add a whole different dimension. And I know that the biological oceanography world is just starting to come to grips with those types of questions. It's very complex.
Okay. Next question from Dom Tolet. Given the 2 to 3-fold higher metabolic rates of juveniles versus adults, were your conclusions specific to juveniles or also adults?
Yeah, they were. That's an excellent question. They're very specific to juveniles, and they were really quite a surprise because, the mantra that most marine mammal scientists hear over and over is marine mammals, their metabolic rate is about twice that of terrestrial mammals, and then you add another 2 to 3 times that for being juvenile. So that was one of the big surprises, is that they really were much lower than you predict. And it might be because, you think of marine mammals, walruses, no disrespect, I love walruses, but they're not bottlenose dolphins. They're not, they're not doing a bunch of high energy things. They're probably in some ways closer to, ecologically almost closer to manatees and dugongs, and they're not pursuing prey. So they don't necessarily need that high level machinery.
All right, next question here. Thank you for that answer. From Zachary Shirker. Wonderful talk. Aside from changes in foraging behavior with varying sea level ice, how are their prey sources expected to respond to climate change? Same fish, just further away, or will there be a dietary shift? Many thanks.
Yeah. So walruses don't primarily eat a lot of fish. So there's a big, I mentioned that because there's a big question around a lot of marine mammals as far as how they'll be affected by climate change. And one of the things you see in a lot of proposals, quite rightly, is something's going to happen to their fish supply, and we don't know exactly what. It could move further away from the equator. It may not. And so it's some people will say, well, it's horrible, the prey is going to move away, and other people will say, well, other prey will come there, or they'll just move with the prey. Walruses are different because they're relying on these sort of stationary prey fields, and we really we don't have enough knowledge at this point to understand what's going to happen to their prey fields. If the problem of pH overwhelms everything else, because they are relying on invertebrates that have shells for a lot of their prey, that could be disastrous for them. If the pH changes so that we no longer have the same degree of shellfish because of the loss of calcium carbonate, that could be a real negative thing to them.
Okay, I'm going to combine two questions here because they're similar. So from Mariana Hill and Jessica Sportelli, basically, are these animals going to be measured again in swimming and resting metabolic rates as they get older, the same animals into adulthood?
Right. Well, that was the plan. So these animals were in Vancouver for about 18 months, and then they went back to the Quebec Aquarium. One of the reasons they were moved to Vancouver was so that modifications could be made to their habitat. But they also had to do some breeding control as far as moving animals around. So they were actually supposed to move to the female we studied and another walrus were supposed to go to another facility where we had plans to continue measuring them. And that was just coming together at about the end of 2019. So the short story is we're still hoping to, because the other measurements that we have, as I mentioned, Andreas Fallman's been doing are on adult animals, and we want to see sort of that transformation. That's really important data for us to get, because young walruses that we can study like this are pretty rare, even in the zoo and aquarium world.
Okay, one more question here in the Q&A and then a couple more in the chat. Daryl, you can jump in maybe after this and then we can go to the chat questions. So this last question from the Q&A, Jessica Sportelli, like before, at what age do walruses start to swim and hunt on their own? Will younger walruses have a harder time in a changing Arctic?
Okay, so I'm going to preface with Daryl's disclaimer that I'm not a walrus scientist. I know they generally are weaned at around 18 months. I don't know how much foraging they do with their mother, like other, phosid seals do before that. They actually they can hang around with their mother for a number of years, up to 4 or 5 years, I believe. So they, you could say they become nutritional independent at about 1.5 years or 2 years. And it's usually tougher for a marine mammal to forage at depth than an adult, just because they don't have the oxygen supplies compared to their metabolism. Now, having said that, walruses I don't want to say they're not great divers. They just don't generally dive very deep compared to other marine mammals. They have, there have been tracks down to 500 meters, but generally they're trying to forage on these rather shallow patches. So I don't know if there's actually a reasonable answer to your question. It's an excellent question about whether they're going to be more impacted of changes in their food. We do know that in general, juveniles are going to live more on the edge. So, your average young juvenile animal may not be significantly affected by an environmental change, but that, 3% that don't make it every year could turn into 4 or 5% that don't make it every year as well. We also don't know if it is affecting. So walruses, one interesting thing about walruses is they're really slowly reproducing species, particularly because their nursing period is relatively long. And so we know among other pinnipeds that you can get extended nursing if environmental conditions are not very good. So we could have a population knock-on effect for that, where it's not so much that something horrible is happening to females or even their young as far as survival, but it's actually, okay, I'm going to nurse through part of another reproductive period. Suddenly your average birth interval is going from 2 years to 3 years, and that's going to have a huge effect on the population. And I'm not sure that there's the data in the field, and again, I'm not an expert on this to answer that, but that could be a more subtle, but in the end significant effect of changes in environmental quality on the species.
Okay, thank you, David. So let me ask you a question about, this is a little ignorance on my part, your methods. And so when you're measuring resting metabolic rate, you say these animals have to be calm, and so what happens? How do you judge when they are, quote, calm and resting, and what's the impact if they're not?
Right. So that's really an important question when you're measuring something like resting metabolic rate, because behaviorally the animal can be not doing anything. So in the past we tended to have this assumption where we're measuring it. If the animal's not pacing, if it's not trying to get out of whatever chamber you're using to measure it, it must be calm and it must be comfortable. And that, of course, is ridiculously untrue in a lot of cases, where an animal can be, it cannot be calm. It can be stressed, but it's not moving. And so, is there any guarantee that you have a calm animal? No, but the more you practice with it, and more importantly, if you can have the animal have the power to break off the measurements, if an animal is in a stress condition, it's not going to want to continue to do that. And so if you set up your experiments where it looks calm, number one, it's familiar with the equipment, so it should be calm, but also it has the ability to say, I'm not enjoying this, I am leaving. Marine mammals are even trickier, because there was a case with another project that I'm on, and I'm not going to name what it was. It was with the faucet animals, and the animals we were measuring it in water, and the animals looked absolutely calm. They were not moving at all. And we were getting these, at first we thought the equipment was broken, because we were getting these, we're getting almost no metabolism. So we're going through all the hoses, making sure everything's connected. And it turned out these animals, not that they were stressed, but they were breath holding, which of course, marine mammals are great at breath holding. So we had an animal that looked perfectly calm, but if you look closely at its nares, it wasn't breathing. And so we'd have these huge periods of essentially measuring no metabolism, then you get a spike. And so you can be fooled by the behavior of the animal. And you just, all you can do is maximize your training, make sure it's a positive experience, which I know sounds very anthropomorphic, which is why you do all these practice sessions with the animals where it's being heavily reinforced for the behavior. So it sees it, quote, as a positive experience. And it also has the option of not doing the behavior if it chooses to do so. And that's really the best you can do. But there are a lot of questions about, I did an undergraduate at University of Guelph with Professor David Levine, who is one of the first ones to take up the pennant that, in fact, marine mammals did not have extraordinary energetic costs, and therefore not higher energy requirements. And looking at the data and saying, how many of these data points were done under the best intentions by scientists and are really accurate, but they're not necessarily on relaxed animals. And so it's a problem. And then of course you get the other side, where if an animal's too relaxed, you're getting sleepy metabolic rate, which is not what you want either. It's a very specific set of equipments that was obviously requirements that were obviously designed by people who worked with hamsters and not people who work with marine mammals, but we do the best we can.
Okay, thank you. Eric, do you have more questions?
Yeah, we have a couple more questions here.
Go ahead.
So this one here from Gary Isaacson. Great research and talk. Are your findings more or less in agreement with the bioenergetics PCOD, population consequence of disturbance, I guess?
Yeah.
Findings by Professor Dan Costa and his team at UC Santa Cruz.
I'm not, to be honest. I mean, I know that the PCOD framework, which is something that's come up for those who on the meeting who don't know that, it's really a way of trying to quantify, again, that relationship between disturbance, some environmental disturbance or perturbation that causes behavior, and how to quantify that in an energetic sense. So it certainly uses that framework. I don't know if they've done anything specifically to walrus. What I've tried to do in discussing my results is within the context of existing walrus models. And the results I found were not outside of the range of values that were used in many of those models. Sometimes they were, swimming, it was on the upper end. But I think that the authors of those studies would agree that, it helps to have specific values for specific age classes for the species that's of concern. Even if you're getting the same values, it just gives you confidence in those values. So I apologize if Dan's group has done something specific to walruses that I don't know of, but it certainly follows the same philosophy.
Right. Another question here from Rebecca Taylor. If these measures for young walruses are so much greater than expected, then the cost of traveling from coastal haulouts to offshore feeding grounds for these young ones really needs to be reevaluated. Given this, do you expect to see measurable changes in young walrus body condition at these autumn coastal haulouts relative to their body condition offshore prior to seasonal ice loss?
That's an excellent question. It's one of the $1 million questions. Do the numbers suggest they're going to have a harder time making a living? Yeah, I have a fairly high confidence in that. I wouldn't be surprised if it does have an impact on the portion of the population that's having difficulty making a living. The problem with going out in the field and seeing that is quite often it's hard to see that portion of the population because of logistics, or they're not making it, or they were not with others. But I wouldn't be surprised if we start to see an effect of juveniles. I also want to point out that one of the things I didn't get into, because it was sort of outside the realm of the study, as far as the impacts of climate change on walrus populations. Of course, one of the big things is when you lose the ice flows, you are going to haul out, and so eventually you haul out on land, and that's what leads to these. It's not unusual for walruses to haul out on land, but we're seeing everywhere these tremendous crowded haulouts of mixed groups, and that's the biggest problem. One of the biggest dangers facing young animals is because you have these tight groups of thousands of animals, including large males. Everything's going on. The females can't seclude their calves from what's going on. If there's ever a stampede, guess who's getting it first? That's also a big thing past the nutritional question.
All right, one last question here in the Q&A and chat. So this one's from Patricia Morris. What are current commute distances for mothers? Given your energetic data, what commute distance becomes a distance too far, where they can no longer gain sufficient energy to cover the commute costs?
That's another excellent question. I'm not sure that the data is available, because it also is going to take a number of ecological and physiological measurements to answer that. Of when is the cost too high, and that depends on how much food is available at the end of your journey, and also how much food you can consume at the end of your journey. So you have a cost, and assuming that cost is below the level of the trip itself is going to kill you, and I don't think we're anywhere approaching that. You have a cost of the foraging ground, and then you go, okay, so I'm at the foraging ground. All I need to do is eat more. Well, there's a physiological limit to how fast you can eat the prey, how much you can digest, what your stomach capacity is. And the longer you spend at the foraging grounds, the longer you're leaving your calf and not nursing your calf. So it's a problem that's seen time and again, particularly for marine odoriids who are not capital breeders, so they have to go on these traveling trips to nurse their young. That's a real problem of how to balance the energy intake and the time away from the pup, and how much can you actually bulk up in order to replenish your energy. So that's an excellent question, and it would be a good exercise, and it's certainly worth doing, but I'm not sure how confident that we would be as a scientific community in the results, but it's certainly something you could look at as far as possible outcomes.
So, David, maybe not a question, but a comment on this last question you just answered. So I did some work with Atlantic walruses in 1980 with Ted Miller from Memorial University. And these were walruses that actually hauled out long before climate change impacts were producing these large haul-outs. These were haul-outs that were mixed group haul-outs. And one of the things that I found interesting is the calves, I think at that point were around 2-3 months of age. Females were nursing their calves in the water. In fact, you would see calves with their flippers up on the female's throat, and clearly were upside down nursing. So any ideas to what extent calves may be following females off foraging and actually still nursing while their females are engaged in foraging as well?
Yeah, no, unfortunately, I don't have the experience of working with them in the field. And so I haven't had those direct observations. And I do, I think that's an important, it brings up an important point where, sometimes we tend to underestimate the flexibility of wild animals. And so we say, well, if they can't do A, they're screwed. And they will work very hard, obviously, to find an alternate way. And not every animal in a wild population reacts the same way. And so when you're looking at population levels and the effects of population levels, you're probably not looking at your average walrus or your average sea lion or your average gray whale. You're looking at, I always like to think of it as, if you're worried about population declines, think about the ones on the tail end who under good conditions are just making it. And those are the ones that are going to be affected. Everyone else might be fine, but it's those ones who are just managing to get through whatever logjam there is in their life history and not making it. So there's, they have a huge capacity for adaptability. And again, I'm not a wild walrus expert, but I wouldn't be surprised if they, most of them, work very hard at doing what they do, and even if they have to find different ways of doing it, but there are obviously limits to what their capacity for adaptation is.
Thanks. I see there's one more question from Louise Huckstadt that we'll go ahead and take, and then it's just after 9. You've done a great job. I've enjoyed your Q&A session as well. So let's go ahead, Eric, with Louise's question, and then we'll say thanks for the talk.
Sounds good. All right, so the question from Louise. Now that you have RMR and FMR for juveniles and adults soon, do you have data on total body oxygen stores and what their ADL would be?
I do not, but I believe there is published data on that. It's not something we were actually proposing to do research with that. It became very complicated to look at that on a developmental basis. I think there is data in the literature looking at the development of oxygen stores in walrus, but I can't give you. I could speculate on the author, but if I get it wrong, I'm in deep trouble with at least 2 people.
Okay, we'll bail you out on that.
Okay.
We'll make you speculate. So let's just go ahead and end by having you tell us what plans you might have for follow-up studies.
Well, as was mentioned from somebody, you know, when the world hits reset, you know, we're hoping to go to. I think it's fair to say, I can probably say it publicly, that we're hoping to continue these studies at the Toronto Zoo, where some of the walruses are going, and also at the Quebec Aquarium. You know, it's, as anyone who's worked within public facilities know, it can be very difficult working within a facility where research is not the prime motivator for having the animals. But we're really fortunate that at these facilities, including the Toronto Zoo, that they have a very strong research program, and they've been incredibly supportive of having us, if we're ever allowed to travel again, having us come there and continue these studies. Because having, you know, just very young walruses and very old walruses is, you know, again, we're speculating what happens in the middle, and so that'd be important to do that.
Well, great, thank you. You've given us a great example of the value of being able to do studies in zoo settings or aquarium settings, or captive settings in general. So thank you very much for that. I appreciate the presentation. I think with that, we'll say good night. Thanks to all for your questions and for tuning in to this excellent seminar we had tonight. Good night.
Good night.